f inverse x and gfx. We need to know what all those things mean and do. Domain and range then. Domain are the inputs into a function. Can't remember that. Domain refer to the x values. And range, the y values, the outputs. So that's what a function is, a set of inputs and outputs, and if you put them all together, they usually form some form of graph. You join the dots to find the graph. Mapping diagrams, that looks something like when you see very basic, you may have seen these maybe when you were in like, you got a function 2x and you got 2, 4, 6, so that maps to that, to that, to that. That's a very simple example. The domain is here. That's a mapping diagram. Perhaps I need to do that again.
I don't remember that.
It's like the set. You would have done it in years 7 or 8. Maybe no.
I remember the coordinates was like 1 and 1.
I did, yeah, you did do it. But maybe you've forgotten. Like you can form a table off this then, 1 to 2, 2 to 4. So this is what it's in the syllabus, mapping diagrams. It very rarely comes up, but this is what it is. Okay. Some example questions then. Would you be able to, in this kind of stuff, if you know input or domain value is 7, can you get the output or range value for that? Yes. Second example question then. They give you 2 functions. Can you get the domain if you know the range? Or is it the range if you know the domain? So what's that then? So it says here, if the domain of the function is between 2 and 4, find the range of each one. You'd have to look at the outputs. You have to substitute in maybe 2, 3, 4 if you want, and then look at what the outputs would be for those, and what's the maximum number you can get, the minimum number you get. So maybe we need to look at domain and range a little bit, which we will. Another type, I think, this is a mapping diagram definition, because I realized I haven't taught it yet this year, but I'll go over it. A mapping is used to map the members of one set called the domain, so the domain, 2 members of another set called the range. And then there's some sort of rule that usually maps the 2 onto each other, and you can put a line between the 2, like this. Some stuff we're very used to then is, in general, if we're given 2 functions, would you be able to form, what type of thing is this called? FG, what do we call that? Oh, you put the g of x into the f of x, it's called a composite function. So you substitute one function into the other and solve. So if I have something like fg, fg of x, it means get the gx function and put it in, I'll rewrite that, the gx function, and put it into the fx function here for the x, put it in. So in this case, we got a gx is equal to 3x minus 1. So I take this and I put it into whatever the fx function is. In this case, it is, so I'm going to put the 3x minus 1 into 2 plus x squared. So instead of 2 plus x squared, I now put this in. 3x minus 1 squared. And I calculate that and simplify it down. Okay, so that's the first, that's stuff that can come up in the first. So substituting one function into another. That's called a composite function. 3.2 then is recognition of different types of graphs. So you might be given something like this. You might be able to, which one is which and why. Which one is the cubic function? Why is x cubed out of these?
Oh my god, I hate these. Oh, it's the R.
It's R, yes, the squiggle, because it's got a double turn in it. Maybe you'll notice that.
Yeah.
Both of these are quadratic type functions, so x squared type functions. But which one is the one in B?
Here.
X squared minus 1. Why do we know it's Q?
Because it just makes sense.
It's a positive x squared. So a negative x squared, Natalia, you good? Negative x squared would be a sad face. And then this one has to be the line, the straight line. You can see it goes through the y-axis at minus 1 as well, so it kind of makes sense here for that one. Okay, here's more of these type of questions from your My Maths. So you'd match maybe the negative x squared one here with this one, yeah?
Yeah.
And then you'd go, which one's the cubic?
The cube.
The cube. And then you have your choice. Which one is one that's...
That one is second one.
This one, yes. It's down 3. If you notice, that's down 3. This one has asymptotes at zeros, which we'll look at in a second. Yes.
Yeah, my math's over.
Yes, of course. Okay.
Is it like 30 things?
Oh, of course. Yeah.
In all of our actual exams, are they all non-calculator or is there one that's calculator?
In your actual exam paper, paper 2, your first exam, will be non-calculator. Paper 4 and 6, calculator. So paper 2, you guys are the first year that'll have a longer paper 2, which means more non-calculator questions than usual. So all the past papers are short paper 2s, but yours will be longer. Just make it more difficult. Okay. Are you back in the room? Not really, kinda. Some of us.
Tell about my maths.
All right. So you should be able to do that. This one then, if you're given something like this, could you rearrange it so you get A, B, and C? This is a difficult one. No, well, you would just do what you did in the last. It's like an algebraic problem. Multiply everything by x squared. No, everything by x squared would be the common denominator, because x goes into that. And then you can solve it that way. You want me to do it now?
Yes.
Okay, I'll do this one.
But if you multiply x squared by x squared, it removes this, right?
So we have this. I'm going to multiply everything by x squared if we're ready. If I multiply everything by x squared, because it is the common denominator of everything gets multiplied. This one becomes x squared over x, which is just x. This one, well, the x squareds actually cancel each other out. 1 divides into 1 once. This one becomes x to the power of 4. Nothing to stop this. And this one, nothing will stop it either. I want it in this form, so I want everything on the same side. I'm going to pick the right side because it's positive. Minus 2x squared, subtract an x, add a 1. And that's my equation. So I know A is negative 2, B is negative 1, and C is 1. Okay? So hopefully that one made sense. I don't know if I have a second example for this one. No, I don't. Finding quadratic functions. So we did a bit of quadratic functions with vertex and x-intercepts recently. No, it's okay. We're going to do this. Back. This is in that form. So it's rearranged. So this is A, this is B, 1, this is C. I just rearrange it. All I have to do is rearrange. Okay, so we need to know, I'll come back to the question in a second. We need to know that this is a general shape of a quadratic. There are two. We got a U shape and an N shape. This point at the bottom or point at the top is called the vertex, or the maximum or minimum. Also called the vertex. It's the turning point. And then through the vertex is the axis of symmetry, where I can fold the function over perfectly on top of itself. So looking at this type of question, if you're given the vertex and the y-intercept, could you form the quadratic? Well, that's where we had our two forms. You might remember this from last year. We had y is equal to x minus h squared plus k with an a in front like this. Remember this? And y, we'll do this again, but I'm just running through it, which was our vertex form and our intercept form. We have to revisit this, which will be one of the things we're looking at. Priyanka, yes?
In like a quadratic, is the vertex like always the same? Like the x point of the vertex always the same as the lines?
Yes. It'd be impossible for it not to be. Has to be in line, yes. Yeah.
For like the exams, will they give this to us or do we have to memorize it?
These, they're not given to you, so you'll have to know it. Yeah. Yes. So you see both these questions are set up to sub into one of these two. So if you know the two intercepts, P and Q. And you'll use, like for this question, you would use this format. And if you know the vertex, H and K, you would use this format. So you have two formats you use, and then you just substitute into these to find the A here. Okay, we mustn't forget the A is crucial because it determines the multiple equations actually go through the same. Like you could have one like this, but you also could have one much narrower that's different, or you could have one wider and upside down that's different that have the same roots. The A determines the different shapes. Could have the same roots or zeros, same intercepts here, multiple ones. So we need the A. That's why we need it. Okay. This is another one. This is one that will come up in your Maya Maths. To rearrange functions so it's written like this, and then you can read off it the minimum or the maximum of the graph. Or these are all minimums. They're all U-shape. That process, if we recall, we can do it using completing the square. Yeah, we did, yeah. Which I'll go through with you again. It's a step-by-step system which changes a quadratic from this step, plus 4x plus 3, into something that looks like this.
Oh, is it like the root thing? Like,
You can use it to solve the equation as well.
so you can do like x plus 2x minus 2? No.
From this completing the square, the quadratic formula comes out. X is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a, and we'll look at that. I know. We're looking at that this week. So when you rearrange it in this form, this will be p and this will be q. We need to go over this. So this is one of the things we need to go over. Okay. Understanding the concepts of asymptote and graphical identification of simple examples parallel to the axis. That seems pretty complicated. But something like this might come up in an exam where we'd have to be able to say what the asymptotes are, or use the asymptotes to sketch. So the asymptotes here, one is at x equal to 2 and the other is at y is equal to minus 2. How will that affect the function? We can look at that kind of stuff. You need rational functions. Functions with a fraction will have asymptotes. All right, Dima. Will have asymptotes. Core is super excited to be here today. Okay, using the graphing calculator to graph, we've definitely done. So you've given a plot like this in the exam, and then the question might be draw this. Like we actually had this one in an exam. Draw something like this using our calculator. Write all the asymptotes in. Write the maximum or the minimum, and then find out where two graphs intersect using our calculator. Real calculator skill on this one.
What the heck? Oh, yeah. Okay.
Oh, Annika's tired. Poor girl. It's a long day, Monday.
I never understood how can the minimum be higher than the maximum?
Yeah, local. It's a localized one. Otherwise, if you didn't localize it, the maximum of the graph would be
The highest point. Oh.
off into space. It's infinity. So the maximum and minimum of any graph is infinity, usually, with this type of one. So that's why they say, oh, where's a local little max or a local?
But is local just like what it shows on your calculator?
Yeah, it's to a specific region, but it's a turning point. It's really a turning point of the graph. So where it turns. So you can see it's turning and going back down. Okay. You good? All right. Simplify expressions. So that's stuff like that. More composite functions and maybe solving a little bit with that. Description using language of Yes, Caleb.
What number does it end? 3 point what?
You'll get there. 3.10. So we're nearly there. Using this, we haven't done this really yet either, so we have to do this. But we did it with shapes, but not with functions. So that's like this. If you got a function, describe the transformation it maps what happens here if you change the x input to x subtract 1 from x to x subtract 1. Well, actually, no, it moves to the right 1 unit. And this one moves down 4 units. Okay? So we have this set of transformations to run through. The second last one then is inverse function. So we looked at that terminology. If you get a bunch of functions, are you able to get the inverse of one of them? That comes up a lot. Swapping x and y, solving for y again. Here's an example from your MyMaths, which you have. Swap x and y. It's a bit like changing the subject of the equation, which we had in the last exam. And the last one, a log as an inverse as an exponential function. This is not log laws. This is not log laws. It is the fact that h of x, 3 to the power of x, when we get the inverse of it, it turns into a log. Or, what you're probably more used to doing is, if we have a calculator, can you solve this type 1? 10